Hello and welcome back to Particleworks Power-ups. Today's request comes from a Formula 1 engineer working on fuel tank design. They told us, "We are using the new Calculate Polygon Motion feature to simulate gates in our fuel tank acting under fluid and acceleration forces. But there is no way to visualize the limits of the constraint to check that they align with our physical stops in the CAD. Please can you write a macro which applies the minimum and maximum rotations to the gate geometry to visually check the constraint is set up correctly." As this is a new feature, let's first take a look at the problem in Particleworks to understand the situation better. Here we have a basic tank sloshing simulation, with acceleration forces in the Z direction shown in this graph. In the centre, we have a gate which is acting under fluid and gravitational forces, such that the gate opens into the left-hand chamber when the flow is right to left, but closes in the opposite in order to keep fuel on the left-hand side. This is achieved using the Calculate Polygon Motion option, along with a constraint which I've applied limits which should line up with these physical stops in my CAD. However, there is currently no way to show the gate at these limits to check the constraint is set up correctly. My plan is to create duplicates of the gates rotated to these limits as markers, which will be deactivated to not interfere with the simulation. Enough explanation, let's get into the code. I'm starting with a standard initialization script with no extra libraries needed. First thing I do is create a list of all constraint node names. This list is then used to populate a drop-down menu in a new dialog box, allowing the user to select which constraint they want to view the limits for. Now we could programmatically add all constraints as Boolean options, like we did in episode 8, or even call this dialog recursively, but for this tutorial I'm keeping things simple and just focusing on the one node. Calling the dialog window in this if statement will cancel the script if the user closes the window rather than selecting a node. Once the user makes the selection, the script looks for the corresponding constraint node by name and loads it into the Python console. From there, I can identify the node target assigned to that constraint. The rest of the code is wrapped in a try block to catch any errors, for example, if the selected constraint doesn't have any limits or something else unexpected comes up. Because the logic is slightly different depending on whether the constraint is rotational or translational, I've used an if statement to handle these separately. If it's a rotational constraint, the first step is to extract the minimum limit. I then duplicate the target node to use as a visual marker, adding min to the name so it's clearly identifiable. I also parent it to the original node to keep the input tree tidy and colour it green for clarity. Before applying any transformation, I update the component center so that it matches the constraint's location. The rotation is then applied by generating a list of values, each being the product of the minimum limit and the constraint's axis value in each direction. To ensure the new object doesn't interfere with the simulation, I set its material to none, effectively making it passive. I then repeat the entire process for the maximum limit, duplicating the target node again, this time changing all references from minimum to maximum and setting the color to be red. For translational constraints, I follow the same approach. The only difference is that instead of applying a rotation, I update the position based on the translation limits, and the variable names and logic are adjusted accordingly. To tidy things up, I hide the original node so only the limit markers are visible. And finally, I add the except statement I mentioned earlier to complete the error handling. That wraps up the macro. Time to save it and test it. I'll begin by deliberately setting the constraint to an incorrect limit so that the problem is obvious. Running the macro is as simple as dragging it into the scene. A dialog window appears and I pick the constraint from the drop-down. Here there is only one entry, but with multiple constraints, each name would match its counterpart in the input tree. After I press OK, the macro shows the gate's maximum limit pointing the wrong way, missing the physical stop entirely. Switching the marker's rotation to the positive value brings it into line, letting me adjust the constraint limit with confidence before the simulation starts. If you have a problem you'd like our help with, our contact details are on screen now and in the description below. For more information about our full API online training course, visit our contact page for details. See you next time.